Alright, in this video I'm going to show how we can decompose a composite function to get back to its original two functions. So suppose we have these two functions. H of x is equal to x squared plus 1, g of x is equal to, 3x minus 4. So if we had h circled g of x, what we're doing is we're taking the g function, putting it into x for the h function, so we'd end up with 3x minus 4 squared plus 1. We can multiply this out. So that's how we perform a composition of functions. Okay, we take two functions and we compose them. What we want to look at in this video is how we go the opposite direction. So how do we take a function that has already been composed and get back to the original two component functions? So let's just see a couple instances of where this happens. Alright, so we have f of x equals square root 5 minus x squared. We want to figure out what two functions, I guess we don't know for sure that it's two functions, but I'll just be explicit. Write f of x as its two component functions. Alright, well, let's see what's happening here. So we have this expression underneath the radical. That looks like something that is a quadratic function or a polynomial function. And then we have the radical. So it kind of seems like we have these two functions. We have the radical function and then we have the polynomial function. So if we were to say h of x is equal to 5 minus x squared, and then g of x was equal to the square root of x, that appears like those two could be the two component functions. And we check this by just actually doing the composition. So this function, 5 minus x squared, looks like it's getting inputted into the g function, into here. So if we say g of h of x, would that give what we want? Well, we're taking the h function, and here this is saying take the h function, put it into the g function. If we do that, that gets us what we want. So that is indeed correct. Alright, the other example we want to look at is writing f of x as its component functions. And again, two component functions. Okay, so it looks like we have a rational function, and then we have this expression down here, which is a polynomial. The rational function has a radical in it. This one's a little bit more complex. Why don't you try it on your own, hit pause, see if you can come up with which two functions this could be composed, or the two component functions that could make up this f of x function. So one option is this, h of x equals 4 divided by 3 minus square root of x, and then g of x equals 4 plus x squared. In this case, if we were to do the g function into the h function, so h circle g of x means we're taking the g function and substituting it in here in the h function. That would give it to us. And that's what we want. I think there's actually another option. If we were to say, so let's give that as option 1. Option 2, I think what we could do is h of x is equal to, there's a few different options. If we did this, 4 divided by x, and then g of x was 3 minus square root 4 plus x squared. Okay, so if we did h circle g of x, we'd be taking the g function, putting it in here, and that would give it to us. Okay, and I actually even think there's a third option. If we did h of x is equal to 4 divided by 3 minus x, and then g of x is the square root function, 4 plus x squared. And then h circle g of x would mean this g function is going in right here, and that would give it to us. That would give us the f function. So, kind of interesting, when I started doing this problem 2 minutes ago, I thought there was only one way we could do it, but there's actually multiple ways, and there's probably even more than what I just came up with. So, the reason we care about this is because when we're doing integrals in calculus towards the end of Calc 1 and in Calc 2, we're going to need to be taking expressions like this and writing them as two or more functions. That'll help us evaluate integrals much more smoothly.